Welcome back. Let us continue our study of planning algorithms. Last time we looked at goal stack planning, and which is an algorithm which breaks up a goal into sub goals and tries to solve them in serial order. And then we encountered this problem that there may be some goals which cannot be broken down into serializable sub goals. And a very simple and elegant example of that was Sussman's anomaly, which we saw here, where the initial state was 3 blocks C on A and B on the table, and the goal state was to get A on B on C, and whichever order of the two goals that we prefer or choose, that either on BC or on AB, whichever we chose first, it turned out that we did not, by the time we solved the second one, we could not achieve the final goal, and moreover the plans were much longer. We saw that the optimal plan in Sussman's anomaly would have been a 6-step plan like this, but the algorithm was unable to find it. Then we observed that if it had started off by searching for one sub goal which is on AB, and then halfway shifted its attention to on BC, solved on BC and then came back to on AB, then it would have found the 6-step plan. But the algorithm does not allow that. It says, the algorithm goal stack planning says, solve one sub goal, and after you have finished solving it, solve the next sub goal, whereas that we have seen does not result in the optimal plan. So, our next approach is to look at an approach of planning which is called non-linear planning. It has got many names, non-linear planning, plan space planning, that is what we will start by calling it. It is also called partial order planning, also called least commitment planning. We will look at these aspects as to why all these different names are there as we go along. So, let us start with the notion of plan space planning. So far, our planning approaches have reasoned with states essentially. So, you had the start state, you had the goal description which amounted to a set of states, and we had operators which took you from state to state. So, it was basically looking at a state and a goal description, and the algorithm terminated if the state satisfies the goal description, in some sense that the goal predicates or the goals were elements of the final state. Otherwise, it searches over the otherwise the algorithm searched over the state space looking for actions to add to the plan, and the plan was kind of constructed as a byproduct, that as you search the state space, you started assembling the plan depending on which algorithm, either from the first action or the last action, but eventually it was a kind of a byproduct of the plan. The alternate view that we want to look at now, consider, is that why not search in the space of all possible plans essentially, and see if that gives us more flexibility in terms of the kind of plans that we can discover. We will call this approach as plan space planning, and let us start off by describing it first. So, the search space in plan space planning consists of what I call as partial plans. A partial plan, so it is a well defined structure, it is got importance of its own in plan space planning. In fact, we only talk about partial plans in plan space planning, we never talk of states at all. Of course, we do talk of predicates that are used to define the start state and the goal state, but never do we represent the state as an explicit object in our program. Whereas, as some people would say, a partial plan is a first class object in the planning approach that we are following now, and it can be passed on as parameter and manipulated and things like that. So, a partial plan is a 4 tuple which is made up of 4 sets which we will call as A, O, L and B, where A is a set of partially instantiated operators in the plan. So, we are simply specifying as to what are the actions that go into the plan. We separately assert as to which actions come before which other actions, and that is specified by something called ordering links. So, here we have an example of A I being before A j or A I preceding A j, and this is said explicitly in the partial plan. Then there is a set of causal links, and the causal links are as follows, that there are two actions A I P and A j, and we say that A I produces P and it is consumed by A j. We will just look at this in a little bit more detail in a moment. And finally, there is a set B, which is a set of binding constraints, which are of the form like x is not equal to y, x equal to y, or x not equal to A, or x equal to B, and so on essentially. I should have added question mark x here, because I want to use the convention that anything before anything which has a question mark as a prefix is a variable, and anything which does not is a constant, because there are two kinds of things that one deals with in a logical kind of a framework. There are some people who say that okay, no, let us just take the convention that x, y, z are variables and a, b, c are constants, but then if you were to write a program, you would have to take care of that explicitly, whereas adopting a naming convention like this is better from the programming perspective. So, just let us expand upon the definition of partial plan. The constituents, as we said, are first is a set A, which is of partially instantiated operators. This set simply identifies as to what are the actions in the plan, and the actions may be only partially instantiated. Remember that we had said that actions are instances of operators. Operators have variables, or operators are like schemas, whereas actions are specific actions which talk about specific objects or manipulating specific objects. But a partially instantiated object like stack A on X says that stack block A onto some block, and the partial planning algorithm allows you to do that, and the plan representation allows you to assert that such an action exists. Now, O is a set of ordering links, as we said. It says that A I precedes A j in this case. So, that converts a partial plan into a directed graph, and we can also see the plan now as a partial ordering on the actions in the plan. So, every time we introduce this ordering link, we introduce some more order into the plan. The causal link is something that I had skimmed over in the last slide, but here is a complete definition. We say that a triple made up of A I, which is an action, P, which is a goal or a predicate, and A j, which is another action, represents the fact that action A I has a positive effect P, which is a precondition for action A j. So, we also say that A I produces P and A j consumes P. A I is the producer of P and A j is the consumer of P. Whenever we will add a causal link like this into the plan, we would also add a corresponding ordering link, because of the fact that time is woven into this connection. A I must happen first, it must produce P, and then A j will use that as a precondition. So, we also add an ordering link whenever we add a causal link. And as we said, B is a set of binding constraints of the form, which are which basically say that variables are equal or not equal, or they come from a certain domain and things like that. Now, when we are doing plan space planning, which is also called partial order planning, we start with a given problem as before. So, we have observed this, that a planning problem is defined by three things. One is the initial state, which must be completely described. One is the goal description, which may be partial in nature, and the third thing is the set of operators that are available to you for making the plans. So, this should have been N here. So, planning in plan plan space always begins with something which we call as an initial plan, and it is always the same structure. So, pi 0 has two actions all the time, which we call as a 0 and a infinity, and it has a ordering constraint which says that a 0 must happen a infinity at it, and it has no causal links and it has no binding constraints. So, a 0 is the initial action which is always present in any partial plan, and it is an action which has, it is a very special action which is devised only for partial planning of plan space planning. It has no preconditions and its effects are the goal, the predicates of the start state. So, in some sense it is producing the start state essentially. So, in some sense that it says that this is where your actions must begin. A infinity is the final or the last action, its preconditions are the goal states and it has no effects. So, A 0 produces the start state or the start goals or the start predicates, and A infinity consumes them. And as we said, there is one ordering link here, this says that A 0 must happen before A infinity. This is the initial plan with which the plan space planning algorithm always begins with. The only thing that changes as we define new problems is that the elements S 1, S 2 and so on, and G 1, G 2 and so on, they change as we move to a different problem, but otherwise the structure is still the same. The initial plan has got two actions, A 0, A infinity, and an assertion that A 0 must happen before A infinity. There are no causal links and binding constraints as we observed, these two sets are empty. Now, there is a notion of something called a flaw in a partial plan. So, a partial plan is called a partial plan because in some sense it is not a complete plan, and if it becomes a complete plan then we call it a solution plan. A partial plan may have two kinds of flaws essentially. The first kind is called open goals, and an open goal is any precondition of any action in the plan that is not supported by a causal link, because when you want to execute an action, it must have its preconditions true, and we have said that causal links provide the preconditions for actions. So, if there is some precondition of some action which is not supported by a causal link, we call it an open goal. The other kind of flaw in a plan is as follows, that if there is a causal link from action A I to action P j and A I produces P and A j consumes P, we say that if this causal link is said to have a threat if there exists another action A t in the plan such that it can potentially delete P, which means that A I may produce P, but A t may delete it, and therefore, A j will not be able to execute. We say that A t potentially clobbers the causal link between A I and A j. Now, plan space planning in all its different variations that people have tried is essentially systematically removing the flaws one by one, and if you have managed to remove all the flaws, then we say we have a solution plan essentially. So, let us now address this question of how to remove these two kinds of flaws essentially. So, the first on the simpler of the flaws is open goals. As we observed, for any action to be applicable, its preconditions must be true, and the preconditions are provided by a causal link. So, any precondition that is not supported by a causal link is an open goal, and we must somehow cater to that. A causal link can be found in two ways. One is that there is an existing action, let us call it existing action A E, and that action produces P that we are interested in, and it is consistent to add that A E happens before A P. This test of consistency is important because eventually the actions have to happen in some given order, and if you have a ordering which is not consistent with what can be implemented in practice, then you do not have a valid plan. So, this consistency check is required, and the simplest consistency check is that there are no loops essentially in the ordering cycles. So, if an existing action AE produces P, then we can add a causal link to that effect. So, we are saying AE produces P and that is consumed by AP, and we also add the ordering link saying that AE must happen before AP to the partial plan. If there is no such existing action, then we look for a new action, and this is the way in which new actions are added to the plan essentially. So, we insert a new action A new, and this action also obviously must produce the predicate P that we are interested in, and we add the corresponding causal link for saying that okay, that open goal that AP had is now supported by this causal link where A new produces that precondition P, and obviously we also add the ordering constraint to the partial plan. So, let us look at this notion of a threat in a little bit more detail. So, here we have a partial plan which has been constructed so far. We have added two actions. We have said that unstack something from A, and maybe that was required so that you could clear A, which means maybe there was something on top of A, and then you want to clear it, and another action pick up A, which follows unstack A, because there is a ordering link between the two essentially. Now, unstack A produces clear A and pick up A consumes clear A. So, there is a causal link which is depicted here in this dashed line essentially. Now, if there is another action we introduce at some point, and let us say this action says that stack B onto something, stack B onto a variable y, and that means stack onto something. Now, it so turns out that because when you stack B onto something, that something will now become not clear essentially. Can that something be A? That is the question that we would want to ask. If yes, then that action stack B y is a threat to the causal link that we just spoke about. We also say that stack B y clobbers the causal link or potentially breaks the causal link essentially. Now, this can happen if there are three things which are true. The first thing is that this action unstack the threatening action stack B must happen after unstack X A. So, unstack X A produces clear A, and after that if stack B happens, then it will delete clear A. And because this clear A has to be consumed by pick up A, for the threat to materialize, this stack action must happen before that essentially. And thirdly, this variable y that we have in this action must be bound to the constant A in the causal link essentially. If all these three things happen, then we say that the threat is materialized. So, we say that stack B A clobbers, it is a terminology which was introduced in the 80s, the causal link. Which causal link? This is the one that we are talking about essentially. And people spoke about declobbering and things like that. So, let us formalize this notion of a threat. We say that an action A threat that can possibly disrupt an existing causal link given by AI P A j, where AI produces P and A j consumes P. It is a threat. Even if it can possibly do this disruption, it is a threat, and we must remove this threat. That is the idea of removing flaws from partial plans. Now, this disruption will actually happen if all the three of the following conditions, as we just observed this thing. One is that A thread has an effect not Q such that P and Q can be unified. This notation comes from the language of logic, and we have been using logic to represent the goals, and we will continue to use the logic. And basically, when we say P and Q can be unified, we can say that either P and Q are the same, or both are of the form of some predicate with some variables, and the variables in P and Q can be unified recursively, then P will become equal to Q. So, by unification essentially we say, can we make the two formulas the same, which would mean that P is the link in the causal link, and not Q has become equal to not P, which means it is broken the link. As we said, A thread happens after AI produces P and A thread deletes it, and A thread happens before AJ. So, A thread has deleted P and it is no longer available for AJ to consume, and then we say that the thread is materialized essentially. How do we resolve a thread? Essentially, what we can do is to eliminate one of the preconditions. So, to eliminate the thread, one needs to ensure that at least one of the three conditions which are required for the thread to materialize is not met essentially. So, this can be done by undoing any one of the three respectively for the three conditions needed for the thread. One is called separation, and essentially separation says that ensure that P and Q cannot unify, then, and this can be done by adding an appropriate binding constraint to the set B in the partial plan. So, for example, we can somehow say that P is something different from Q. Remember, P is the link proposition in the causal link, and Q is the not of Q is actually the effect of this threatening action. Or we can move the action A thread to happen before it can disrupt the causal link, and we call this as promotion. We advance the action A thread, and we do this by adding a ordering link which says that A thread must happen before AI to the set of the partial plan. So, you can see that essentially we are looking at this plan as an explicit representation, and we are manipulating that representation, and in that sense a partial plan is a first class object which we can manipulate. The third thing is called demotion, which says that the action A thread should happen after the causal link has been in some sense consummated, and we can do that by saying that AJ, which is the consuming action for the causal link, happens before A thread. So, AJ has finished consuming P, and now it no longer matters whether A thread happens afterwards and destroys P. So, here are this example for the thread that we saw. We can reduce this thread. Remember that this thread is saying that not clear Y and clear A, that link is being broken essentially, and we are saying that make sure that stack By happens before unstack Xa, then the thread will no longer be there, and we say this method of resolving the thread is called promotion. The other way to do is to say that this action which was consuming the predicate happens before the threatening action, so that it has finished consuming it and the threat no longer materializes. And the third thing we can do is separation. We say that this variable Y should not be able to bind to the constant A, in which case it would, the stack action would remove this clear Y, but that Y would not be A essentially. We have seen this basic algorithm for plan space planning. So, what is the algorithm? Just let us do a recap. The algorithm says that start off with the initial plan, which contains the initial action A0, which produces the start predicates, and the final action A infinity, which consumes the goal predicates. Keep inspecting this plan, keep looking for a flaw, and keep resolving the flaw. So, that we said there are two kinds of flaws. One is open goals, they can be resolved by either establishing a causal link with an existing action or by adding a new action which will provide a causal link. The other kind of flaw was a threat, and a threat essentially threatens to break a causal link, and we said that we can resolve this flaw either by making sure that this threatening action happens before the causal link comes into effect or after it has been consumed, or making sure that it does not break the causal link by saying that a variable is bound in an appropriate manner. So, now let us take up an example of this process and see how partial order planning or plan space planning, as we have been calling it, finds a plan. We will do that in the next session.